Hello, so in this video I'm going to be introducing the derivative um, using the definitions. So let's say that we consider the position function uh, like in the very first section where we looked at s of t equals to negative 16t squared, but we're going to use a different initial velocity, I think. 128t, um, and that's it, yeah. And this is going to be at the ordered pair 1 comma 112 that we're interested. So suppose that we want to find the instantaneous velocity. Well, I know that basically I just need to do where I have the limit as t approaches 1 of s of t minus s of 1 divided by t minus 1. Now, accordingly, we know that s of t is equal to negative 16t squared plus 128t minus 112. Now, all of this is divided by t minus 1, so we have t minus 1. Okay, so essentially we have that in finding the instantaneous velocity, we're going to need to basically factor. So we have that if we take, let's see, okay, so this is going to be negative 16 times t squared, and this should be minus 8t, and this will be plus 7. Okay, so here we have that this is going to give us t minus 1. Okay, but we note that this is negative 16 t minus 1 multiplied by t minus 7, and all of this is divided by t minus 1. But notice that a factor cancels out, so we have that this is actually equal to the limit as t approaches 1 of negative 16 times t minus 1. And when we take the limit, we end up with, this should be 7. Yeah. So when we take the limit, that gives us 96 feet per second. Okay. So that represents the instantaneous velocity. But in our little preview of the first section, we also mentioned that basically this is also the slope of the tangent. Now, we have like several definitions essentially for instance, we know that the average rate of change, for instance, so the average rate of change, that's given by what we call the secant, which is equal to f of, well, we'll just say f of b minus f of x divided by b minus x. However, we do have that we have the instantaneous velocity. So in this case, like if we have the instantaneous velocity, so we'll just say instantaneous velocity. Well, essentially that's really just taking the limit as x tends to b for f of b minus f of x all over b minus x. Now, this is actually equal to what we call the tangent. So we can say that this is the slope of the tangent. So these two are related, but it requires taking the limit. Now, let's do an example of where we look at, how we can find the slope of the tangent at a particular point. So, for instance, let's look at, okay, so let's say that we want to find the slope of the tangent for f of x equals to 2 divided by x at the ordered pair 1 comma 2. Okay, so this is actually not too bad because essentially all that we have to do is just say that, well, we have that the slope of the tangent is equal to the limit as x approaches 1 for, okay, so we're going to have 2, so we'll have 2 minus 2 over x, and all of this is divided by 2 minus x. Now, note that, for example, that if you plug in 1, you get 0 over, hang on, this should be 1, actually. Yeah, okay, so that should be 1. Let's just change that real quick. Okay, so this will be equal to 0 over 0, which is basically indeterminate. But we learned that essentially we can switch, or we can eliminate the fraction by multiplying by x on top and bottom. So let's do that. Let's just multiply by x, and we'll just multiply by x. What this does is it gives me the limit that not t, but x is approaching 1, and this will be 2x minus 2 divided by 1 minus x, and this is multiplied by x. Now, furthermore, we have that this is going to be 2 times x minus 1. But notice that basically the 1 minus x's, they do cancel out. Or at least the 1 minus x with its conjugate or opposite. So you have that cancels out, and it leaves you with just negative 1. So you're left with negative 1 because those two are complete opposites. So when you simplify it even further, you have that this is going to be equal to the limit as x approaches 1 of negative 2 over x, but when you take the limit, this equals to negative 2. So that means that the slope of the tangent is equal to negative 2. But if you wanted to find, let's say for example, the tangent line, well, you would have to basically use y minus the function value, so like y minus 2 equals to negative 2 times x minus 1. But in this case, this gives you y equals to negative 2x, let's see, plus 4. So you have that the tangent line is negative 2x plus 4 as well. So, and you can check your work by plugging 1 back in. So right here, this is equal to the slope of the tangent, and this right here is the tangent line. Okay, so we have that that's the tangent line. Now, if you want to, let's say, you use a different definition, you actually can for the slope of the tangent. So it doesn't necessarily, restrict us, because we have that there is, yes, alternate definitions for the slope of the tangent. The slope of the tangent can be given by the limit as h approaches 0 of f of, okay, we use b back there, but let's just use an a. So a plus h minus f of a divided by h. So this is more or less the exact same thing. So let's say, for example, that that we use this alternate definition for finding the slope of the tangent. Okay, so what this is let's say that we have a specific function that we want to work with. So we'll just say find the tangent line um, find the tangent line at x equals 2 for the function f of x equals to x squared plus 2x. Okay, so looking at this, we see that we have that f of 2 is going to be 2 squared plus 2 times 2, which is actually just equal to 8. So that tells us that the ordered pair is just 2 comma 8. So let's go ahead and find the tangent. So we have that the tangent is equal to the limit as h approaches 0 of, well, this is where it gets a little interesting. We're going to use 2 plus h squared plus 2 times 2 plus h minus the value that we get when we plug in 2. So we get 8, and all of this is divided by h squared. Or not h squared, but just h. Now, this is where we have to use a little bit of algebra, where we simplify a little bit. So we have the limit as h approaches 0 of 4 plus 2. Well, really, it's 4 plus 4h plus h squared plus 4 plus 2h. And all of this is going to be minus 8. Now, notice that everything is divided by h. So in this case, we have that the 4 cancels out because 4 plus 4 is 8, and that's going to be minus 8. So what this does is it gives us that we have, let's see, you have the limit as h approaches 0 of 6h plus h squared all divided by h. But another factor of h cancels out, so we have that that's the limit as h approaches 0 for 6 plus h. But furthermore, that gives us the slope of just 6. So we have that the slope of the tangent is 6 units. Okay, so in calculating this tangent line for x squared plus 2x, we would use the formula. So we have that y minus 8 equals to 6 times x minus 2, which in this case is going to be y equals to 6x. Okay, so that's going to be 6x minus 4. Okay, so this is going to be our tangent line, 6x minus 4. Okay, so this is our tangent line, and that's the slope. Okay, so that was not too bad, but again, that was using this alternate definition right over here, which, I mean, it's really preference on like whether you want to use this one or the other one. I prefer basically the one that I don't have to use, where I have to expand this binomial, which that I kind of did really fast. So if you're wondering like how did I get that really, you can just take 2 plus h and multiply by 2 plus h. So the problem with this is that we would need to FOIL versus like the other alternate definition, you would have to factor, but that's not too bad. Okay, now the next thing of which that we can look at, for example, is to give a little bit of notation. So in a way, we have that we're still calculating the slope of the tangent, but we only give it like a new name, for instance. Okay, so we are more or less just calculating the derivative. So this next definition is essentially just finding the derivative of a function at a particular point. So we write such as like f prime of a is equal to the limit as x approaches. Okay, so this is going to be very similar to my original definition, but I'm going to switch the signs. So I have f of x minus f of a divided by x minus a. This is one of the, okay, so this is derivative at a point. So this is the same thing as the slope of the tangent, but it's just written a little bit differently. Okay, but you also have that you can use a different definition. So that's going to be or, okay, so you have f prime, so I'll just put it right over here. F prime of a equals to the limit as h approaches 0 of f of x, not x, but a. Okay, so f of a plus h minus f of a, and all of this is divided by h. Now, this is provided the limit does exist. So you have to be careful with that, that it's provided the limit exists. But if f prime of a does exist, then we just say that f is differentiable at a. So this is a sort of introduction to using, yeah, using uh, yeah, using derivatives. Okay, so and note that this right here is still the secant. It's just different because essentially what we're doing is we're just saying that we can actually just take a curve in the x and y plane. So like for instance, we could have something like this, but we're only looking at the point A and the point A plus h. So in this sense, what we're looking at here is 2 points. So here I have that delta x is right here. That's the change. But then this little increment right there, that's the delta. That's the delta y. So essentially, we have that the slope is equal to the delta y over the delta x, but that gives you basically just f of a plus h minus f of a divided by the change in x, but the change in x was just that constant h. So in this case, we have that it's more or less the same exact thing because we're looking at the point at a, of which essentially all that we need to do from there is just take the limit. So we have f prime of a is equal to the limit as that increment gets smaller and smaller for f of a plus h minus f of a all over h. Okay, so essentially we just have to make sure that this limit does exist. Okay, so let's work on an example of where we try to find the derivative of a function at a particular point. So I want to find f prime. Um, yeah, I want to find f prime of a. Okay, so in this example, we're going to say that f of x is equal to the square root of x plus 1, and we're going to say that a is equal to 3. Now, note that if you were looking for the tangent line, you would actually need to find the ordered pair that corresponds to that, which in this case would be 3, comma 2. But let's just go ahead and just find the slope for this one. So to do this, we're going to say that we have f prime of 3 equals to the limit as h approaches 0 of f of 3 plus h minus f of 3, all divided by h. But I just mentioned that basically you have the square root of 3 plus h plus 1 minus f of 3, which is just 2, and all of this is divided by h. But this simplifies to the square root of 4 plus h minus 2, all divided by h. Now, it becomes a question as to, like, how can you figure out the limit of this, because if you plug in 0, well, you get 0 over 0. So once you kind of just reduce this first off, okay, so let's just put the square root of 4 plus h minus 2 divided by h. The next thing to do is to multiply by the conjugate. So you have 4 plus h plus 2 divided by root 4 plus h plus 2. But this equals to 4 plus h minus 4. And all of this is divided by h multiplied by root 4 plus h plus 2. Just close it. Now, we see that basically the 4's cancels out, and also a factor of an h cancels out too. So this simplifies a little nicer. So this is the limit as h approaches 0 of 1 divided by the square root of 4 plus h, and then that's plus 2. But if you take the limit of that, you end up with 1 over, well, that's just root 4, so that's 2, so that's 2 plus 2, but that equals to 1/4. So that means that the slope of the tangent is equal to 1/4. So that's actually not too bad. So where I'm going to try to leave you is that I want you to basically just try using the limit as x approaches 3 of, so in this case you would have the square root of x plus 1 minus, okay, so minus 2, and then all of this would be divided by, let's see, that would be divided by x minus 3. Okay, so when you do this, try to see like what you get. It will simplify nicely to 1/4, but just try it. And then try to find the tangent line as well. So remember that the tangent line is f of a, well, y minus f of a equals to f prime of a, since now we know that f prime of a equals the slope of the tangent, multiplied by x minus a. Now, you may be wondering, like, why do we even need this, for instance? Well, if you are, then basically it kind of gives us an idea of how we can estimate things, such as like if we have the square root function, and then let's say that we know that we're going to try to, like, say for example, estimate root 5. Well, root 5 I don't know, but I do know root 4. So like if for example that's 5, and then we have that there's a tangent that lies right here. Okay, so let's just imagine that that's it. So in this case, like if we knew that this was the function y equals f of x, then in this case I would try to estimate how I can get the square root of 5. So for instance, I know that the delta x, or the h, is equal to 1, okay, but we can get there in a little bit, because for instance I know that the ordered pair at 4 is 2. So that means that I have, that's going to be 4 comma 2. Now you're going to learn that basically that f prime of 4, well, f prime of 4 is essentially, right, and this is the square root of x. F prime of 4 is essentially 1/4. Okay, so you have 1/4. And then you have that this is going to be y minus 2 equals to 1/4 multiplied by x minus, well, in this case, 4. Now, notice that if you were going to use that x was 5, then basically that would mean that you're trying to say that the square root of 5 is going to be as follows. Y equals to 1/4 times 5 minus 4, and that's going to be plus 2. But that equals to 2.25. Now, notice that if you square 2.25 in your calculator, when you square 2.25 in your calculator, you're going to get 5.0625. Now, this is not a perfect estimate, nor was it implied that it was going to be, but it's close. So we see that this is actually pretty close to our estimate, or I'm sorry, well, it's actually pretty close to the true value of whatever the square root of 5 is, because the true value of the square root of 5 is 2.24 or 2.236. 2.236 is approximately the square root of 5. So in that case, notice that we're only off by a little bit, but notice the error that we have here. So in this case, we can either say that the error is 2.25 minus 2.236, or we can just say that the error is from when we squared it. Let me just go ahead and write down what the error is. So I'm finding that the error is, okay, so the error is approximately 0.0139, and that's not too bad, okay, but we can minimize that if we get a closer estimate. But at least this kind of gives you an idea of how we can use the tangent line for estimating. So when we come back to the next section, which is the definition of the derivative, or derivative as a function of x, you're going to basically kind of see like how we can use several different functions and kind of do the exact same thing. Because as long as we can get that delta x to be small enough, so delta x must be 0 basically in order to get this to work in this case. So the delta x being 1 was not a big deal, but apparently there are better ways that we can estimate this. Okay, so this kind of gives you kind of a clue on terms of like how you can use the first derivative to estimate some things, and also to find like how fast something is moving, for instance, because we did mention that with the position function it's distance over time, which basically is average velocity, but yeah, when we take the limit we get the instantaneous velocity, so that's the velocity function.